Just like we had a common ion effect with pH, we also have a common ion effect with solubility. And with the pH, it generally always raise the pH for acids, but the common ion actually can affect solubility in different ways. So it depends on what the ions are. So we're going to look at that. Let's calculate the solubilities in the presence of other ions. Okay, so for example, you want to know what is the solubility of calcium oxalate in a solution of calcium chloride. So let's write that out, calcium oxalate. Calcium plus oxalate. That's the solubility we're worried about. But we want to know how much of it will dissolve if we already have calcium around. So if there's already some of this calcium from a different source, from a common ion. So the calcium oxalate will produce some calcium, but the calcium chloride also gives some. Now the calcium chloride is a soluble salt, so we're not worried about the chloride, but if we have more calcium. So just when we talked about equilibrium before, let's say we add some of this calcium, what happens? The equilibrium shifts to the left. What does that mean? That means less of the calcium oxalate will dissolve. So it makes the solubility, a common ion will make it less soluble than it would be in pure water. So let's actually look at this as an example. What is the molar solubility of calcium oxalate if it's put into a 0.15 molar calcium chloride solution? The KSP for calcium oxalate, we actually found that earlier, is 2.3 times 10 to the minus 9th. So again, if we set up our equilibrium expression, so what we're looking at, we don't really care about the calcium chloride. We just know that that's present. So it's still the solubility of the calcium oxalate. So that's the equilibrium that you want to set up. You're not going to include the calcium chloride because we're really talking, again, I think this is the hardest thing to understand. We're talking about the solubility of calcium oxalate. We're just looking at it, the fact that it's got 0.15 molar of calcium already in it. So the initial starts out at 0.15 calcium. And I know a lot of people want to put the chloride in there too, but that's not part of the equilibrium. It's only the equilibrium of the calcium oxalate, and the calcium does affect that. The chloride has nothing to do with it, so we're just ignoring it in this case. So again, our solubility is minus x, so we'll have adding x, because it's 1 to 1. So at equilibrium, we have 0.15 plus x and x. So if we plug that into, we have KSP 2.3 times 10 to the minus 9th equals 0.15 plus x times x. We're going to have to do a little algebra. So we're solving for x. We're going to assume that x is going to be negligible compared to 1,5. Now, if you don't want to assume that, you can solve the quadratic equation because you'll have an x squared term. But since most of these solubilities are pretty low, we're gonna assume it's expected to be negligible. So we're gonna ignore it here. Now we can then compare at the end and say, oh yeah, that's true. So we don't want to just leave it hanging, but we're going to say assume x is much less than 0.15, so we can drop it. And if we solve, then we get 1.5 times 10 to the minus 8th. And yes, indeed, 1.5 times 10 to the minus 8th is much smaller than 0.15. So x is negligible in comparison, but we can find out what x is. So if you remember from earlier, the solubility of calcium oxalate is much, much smaller than it was in pure water. So the molar solubility of calcium oxalate in calcium chloride is 1.5 times 10 to the minus 8th molar. In pure water, it was 4.8 times 10 to the minus 5th molar, and realize that's over 3,000 times greater solubility in the pure water. So this definitely made something much less soluble. And so the other, we're going to look at it now look at the precipitation from the other point of view, or where we have the ions in solution and now we make a precipitate. That we were looking at it for something that was solid that was dissolving, and now we're looking at the other way, making a precipitate. So rather than considering how much will dissolve, we ask the question, will a precipitate occur, giving the starting ion concentrations? Because sometimes you can mix two things and nothing will happen. If you add a little bit more, eventually you get a precipitate. So we're going to look into that. So to do that, we're going to look at the reaction quotient, or the Q value. If you remember that from chapter 13 with equilibrium. So we can compare Q to K. What's the difference? K, we know, is the expression of the equilibrium concentration, and Q is written in the same exact manner. We just don't necessarily know if we have equilibrium concentrations or not. So they could be the starting values or the values in question, and then we compare Q with K to see if well, in the old case, we would say, does it go to the right, does it go to the left, or is it at equilibrium, which is the same thing we're going to look at here. So if we consider this, go back to our lead chloride, what is Q? Q will be the same as what K is, only, we just have initial values or non-equilibrium values, or we don't know if they're equilibrium or not. So we're not assuming they're equilibrium expressions, but we're just putting in what the concentrations happen to be, and we can solve for Q. If Q is larger than K, then in order for Q to get smaller, the equilibrium will need to go to the left, right? Because if Q is a large number and it's trying to get smaller, then both the values have to get smaller, which means it has to go to the left, which means precipitation occurs. If Q is less than K, it means the equilibrium is shifting to the right, and we can still dissolve more, so we probably won't have a precipitate. And of course, if Q equals K, that's the very exact point that the solution is saturated, and actually the very point that precipitation will start to occur. So that's what we're looking for, is what are the concentrations that will just make the precipitate occur. So let's look at an example. The concentration of calcium ion in blood plasma is 0.0025 molar. If the concentration of oxalate ion in the blood is 1 × 10⁻⁷ molar, do you expect calcium oxalate to precipitate? Or we could say, do you expect this person to get a kidney stone? Anyway, so the KSP for calcium oxalate, as we've seen before, because it's the same one we keep looking at, is 2.3 × 10⁻⁹. So we can set up our Q value, right? Q is the calcium concentration times the oxalate concentration. They don't have to necessarily be at equilibrium. They're just the concentrations we know. So let's plug those values in. 0.0025 for calcium and 1 × 10⁻⁷ for oxalate. So Q is 2.5 × 10⁻⁻. So then we need to compare. And in this case, Q happens to be smaller than K. So that means, because it's an order of magnitude, so it's about 10 times smaller than K. So we're not going to get a kidney stone this time. More of the calcium can dissolve. Even if we ate a little bit more calcium, we can dissolve it. So no precipitate will occur. If Q was bigger than K, then some of it would have to precipitate out. So I just wanted to do another quick example just to show you kind of from the start what other kind of problem you might get and how you go about it, especially if you don't know what the precipitate might be. So let's look at this example. Predict whether a precipitate will form if you mix 175 milliliters of 0.0055 molar KCl with 145 milliliters of a 0.0015 molar AgNO3 solution. Identify the precipitate, if any forms. So what we have to do is first figure out what could the precipitate possibly be? Is there going to be a precipitate? And then we have to use our Q expression to find out if the concentrations are big enough to form a precipitate. So we kind of have to use our solubility rules, and we have to use some concentration changes, because we're changing. We can't use these concentrations that are given, because notice that we're mixing volumes, so our volumes are changing, and so our concentrations will also be changing. Anyway, the first thing we want to do is see, okay, we're mixing KCl and AgNO3, so what will that give us? And we have to decide if there will be a precipitate and what it will be. So if you remember, now this one's kind of a straightforward one, because everything's 1-to-1, but if you mix KCl and AgNO3, swap partners, and we get KNO3 and AgCl. Ag is a +1 ion. So from our solubility rules, we know that anything with potassium is soluble, anything with nitrate is soluble, and that most chlorides are soluble except silver is an exception. So we know that silver chloride is a possible precipitate. So if a precipitate forms, it will be silver chloride. So now we can ignore the potassium, we can ignore the nitrate. All we want to do is figure out the equilibrium of our insoluble compound, which is the silver chloride. So what we want to do is get the Q expression for the silver chloride, and then find out what our concentrations are, plug them in, and then you can compare it to KSP. Now that we know what the precipitate might be, we can look up on our table back a few slides ago and find out that the KSP for silver chloride is 1.8 times 10 to the minus 10. So now we have something to compare it to. So now that we know what the reaction is, we're just going to write the reaction that we're worried about. So again, we don't need to include the potassium, we don't need to include the nitrate, because they have nothing to do with solubility. They're kind of side ions. So our solubility reaction is just the silver chloride as a precipitate. Of course, we're looking at it going in the left-hand direction. What concentration of ions are required to start the precipitate process to make the solid silver chloride? Our Q expression, Q equals silver concentration times chloride concentration, and of course the I just means initial, because we don't know if we're at equilibrium or not. We're going to compare it to equilibrium. And so now, though, the problem is that we need to know the molarity of the silver and the molarity of the chloride before we can plug it in. And part of the, if you think about this problem, we're adding, we do know a concentration of KCl, and we do know the concentration of AgNO3, but we don't know exactly the concentration of silver or chloride, because when we mix them together, there's going to be a dilution as well. So we can't use these concentrations. We have to rethink through what it is. So the silver concentration, then, we take the volume of the silver nitrate times the molarity. That will give us moles. And then if we divide by the new volume, which is the sum of the 175 milliliters plus the 145 milliliters, we'll now have 320 milliliters of our final solution. So take the volume of the silver times the concentration of the silver nitrate divided by the total solution, and we get 6.8 times 10 to the minus 4 molar. And then the chloride would be the 175 milliliters of the KCl times the 0.055 molar KCl, and then divided again by the total concentration. Now, it may seem like that's not necessary, but it really depends on the Q expression. In this case, because our Q, everything's 1-to-1, it works. But if you had to square one of the units or one of the concentrations, you want to definitely make sure that you go through this process to get the concentrations correct. Also, I'll point out that you don't have to convert this to liters. Technically moles is molarity times volume in liters, but because you're dividing again by by volume. If you wanted to, you could leave this as 145 milliliters and leave this as 320 milliliters, and they would cancel out anyway, so it doesn't matter. You'd still get the same answer. So anyway, now we know the new concentrations of the silver and the chloride, so we plug those in the Q value and then compare it to the K value. K was 1.8 times 10 to the minus 10, so that's definitely much smaller than Q, and since Q is larger, in order for Q to get smaller, it has to precipitate. So we will get a precipitate, and that precipitate will be silver chloride. So other things might affect the solubility besides the common ion. So like we saw, the common ion shifts equilibrium to the left, meaning that less of the salt is soluble. pH can actually affect the solubility in a number of ways. So again, it depends on if the salt has some acid-base character to it, whether an acid or base solution will help it dissolve better or not. So if we have a salt, and we just studied in the last chapter, you know, which salts have base characteristics, which salts have acid characteristics. So again, going back to those 6 strong acids, if the positive, let's see, 6 strong acids, if the negative ion is one of those 6, then we don't have to worry about it. But if it's any other negative ion, we do have to consider its basic properties. And then also with the positive ions, if it's any of the 6 strong base positive ions, we can ignore them. But if it's any other positive ion, we have to consider its acidic properties, because all the conjugate bases of weak acids can react with acid, with H3O+. And so we will expect solubility to be affected by pH. In some cases, it might make it more soluble or less, depending on what the salt is. So if we go back to our calcium oxalate. So oxalate, the calcium is one of the 6 strong base ions. So we don't have to worry about it. But the oxalate comes from a weak acid. And so C2O4 negative 2 is basic. It comes from a weak acid, HC2O4 negative. And so if you add acid to your to the water, to your solution, you can see that some of the oxalate will react with the H3O+ to form the conjugate acid. And so in effect, what you're doing, if you add acid, if you try to dissolve this in acid, what you're basically doing is removing some of the oxalate ion, reacting it in a side reaction, removing some of it. So what does that do? It shifts equilibrium to the right, and that makes the calcium oxalate more soluble. So I guess if you're prone to kidney stones, you might need to eat a little bit more acid somehow. I guess I'm being facetious there. So, but it could have to do with pH balance. So this is saying exactly what I just said. According to Le Chatelier's principle, as the C2O4 ion is removed, more calcium oxalate can dissolve. So we expect a salt that has a negative ion that comes from one of the weak acids to be more soluble in acidic solution rather than pure water. Limestone caves are actually an example of that. So acidic groundwater will dissolve limestone, but then when it when it gets down underground, the calcium carbonate will reprecipitate, and so that's where these stalagmites and stalactites come from.